All right, thank you. Hello, everyone. Good afternoon. This is Derek Hengeveld with Veritrek. Also talking today will be Jacob Moulton. So at its core, Veritrek is a reduced order modeling software tool. Basically what it does is it enables you to convert your thermal models into a reduced order form, and then by running off of the reduced order form, we can run simulations very, very quickly. So we can run thousands of simulations in just mere seconds. And so what we're going to be talking about today is basically half of that software tool, which we call the creation tool. And so that's the part of the software tool that allows you to convert your model into a reduced order form. On this title slide, we've got a couple use cases, some success stories. We've had a lot of users that have been using it for a variety of reasons. We've had NASA JPL. They've been using it for their Mars 2020 helicopter. If you are available tomorrow morning, I'm going to be giving a talk about some of that work. They use that for some sensitivity studies, and actually we'll be using that for mission operations. We also had ATA Engineering use it for design optimization. FNC used it for design verification, and NASA MSFC used it basically to generate a response surface. So with that, we're going to jump into the Veritrek creation tool. Jake, if you move to the next slide, please. Before we do that, just a quick aside about LoadPath, which is basically the parent company that created Veritrek. We're a small business, about 25 employees, located out of Albuquerque, New Mexico, with some satellite offices. We do mechanical design and analysis, structural testing, deployable structures, and thermal hardware and analysis. We can move to the next slide, Jake. Just some of the things that we do provide on the thermal side. We do thermal hardware, things like small sat deployable radiators, thermal energy storage panels, high thermal conductivity, lightweight thermal straps, and we provide thermal desktop analysis services, CubeSat modeling, gimbal modeling, sequencer modeling, just some examples of some of the work that we've done in the past. All right, so let's jump into what is Veritrek. And before I do that, I just want to quickly mention that if you do have any questions, we're monitoring the chat window on the live stream, so feel free to just type in a question and we'll gladly field those questions, stop our conversation. So basically, Veritrek, what it does is it converts your thermal model, specifically your thermal desktop model, into a reduced order form. It's basically a three-step process. You start with your high-fidelity thermal model. We see that in the upper left. Then we use the Veritrek creation tool, which converts that model into a reduced order form. And in this talk today, we're going to go through what that looks like. How do we actually interrogate the thermal desktop model? How do we convert that into a reduced order form? What are the steps involved? What are the costs involved with that? And what are some of the capabilities of that process? Once we have that reduced order model, then we can use our Veritrek exploration tool to do something valuable with the reduced order model. The exploration tool, we're actually going to go do a deep dive into that tool tomorrow morning if you're available. I think there's a video here. We'll take a look at what that exploration tool looks like. Basically, at this point, we've converted our thermal desktop model into a reduced order form. And what we're doing here is we're changing some of the parameters in our thermal model, in our reduced order thermal model. You can see the user here is changing these slider positions. Essentially what's going on is we're changing symbol values in our thermal model. And what's going on the right-hand side is that we're generating a response surface based on two input factors and one output response. So every time we're moving that slider, we're basically generating a new and unique response surface. The back of the scenes, what's going on is we're running 400 simulations to generate that response surface. And you can imagine the computational expense involved in doing that with traditional methods. But by first converting our thermal model into a reduced order form, we can generate response surfaces, almost in near real time. So hopefully you can start to see some of the value of reduced order modeling. All right, let's move on to the next slide. All right, so why Veritrek? Hopefully you've started to see some of the reasons behind it. We have our powerful thermal modeling tools. They're high fidelity tools. They can do a lot. Thermal desktop is kind of the world that we typically live in. It's a highly capable tool. It has, a lot of functionality. Pretty much whatever you throw at it, you should be able to model it. The simulations, they can take minutes to hours to days to run a single simulation, and in a lot of cases that can be one of the most significant costs, and it might limit a user to running essentially stacked worst case analyses. But if we can convert that model into a reduced order form, we can then run thousands of simulations in seconds, and it really opens up some of the analysis types that we can do. And so we see some of these analysis types that are provided with Veritrek. We have a point analysis in the lower left, kind of a spreadsheet type approach. We have 2D plotting capabilities. We have a response surfaces, which we've already seen. We have a correlation feature, a rapid correlation feature that is in beta right now, but we're hoping to roll that out pretty soon. We have a screening analysis feature and then also an optimization analysis feature. And you take all of these and you fold in thousands of simulations in seconds, and you get some expanded analysis and improved understanding. So Jake, we can move on to the next slide. All right, so what is a reduced order model in our eyes? You know, in a lot of cases, we're taking multi-thousand node models and we're reducing node count. What we're actually doing here with Veritrek is we are basically sampling and then data fitting. So we're running our high fidelity model at a number of different sampling points, and then we're fitting the resultant data. So we have a very simple example here, a 2D example where we have one input factor on the x-axis, and we have one output response on the y-axis. And so let's say we wanted to generate a reduced order model that would basically correlate these two parameters. What we could do is we could run our thermal desktop model at a number of different input factor settings. Let's say our input factor is heat load. So we run it at, let's say, 0, 1, all the way up to 5 watts. And what we want to do is track an output response, something like temperature of a node. And so we do that. We run our thermal model at 6 different points. We generate these red circles, or what we would call training data. The next step then would be to fit that data. And it looks very linear, so we put a linear fit through it. We come up with this equation, y equals 10x plus 10. And so, if a question came up of, what is the output response at a non-sampled point? So let's say at an input factor of 3.5 watts, what would be the output response? Well, we could rerun our thermal desktop model. But again, there's some computational expense involved with that. So why not just use the model that we created, this equation, and we can simply plug in 3.5 in for x, and out comes our output response of 45 very quickly. And so that's essentially what we're doing. We are sampling, so generating the red circles here, and then we're data fitting, so generating a fit through the data. Except with Veritrek, we're expanding that quite considerably. We have multiple input factors, not just one. We have, upwards of maybe 10, 11, 12, which really is dependent on the model complexity and, a number of other factors. But typically, the kind of the upper end that we've seen so far is 10, 11, 12 input factors. We have multiple output responses. Some of the work that we've done, for example, the Mars helicopter, we had, I believe it was 36 output responses that we were tracking. We also have, within Veritrek, we have sampling algorithms that kind of do the heavy lifting for you, that help sample the design space very efficiently. And then one of the bigger challenges with this type of approach is just the model fitting. How do you fit data that you really don't know what shape it is? In this case, it was very clear that it was a linear data, so easy to fit that. But what if it's a nonlinear system that we often run into with thermal? We need a fairly robust data fitting scheme. So Veritrek provides that behind the scenes. All right, Jake, we can move on. All right, so with that, I'm going to turn that over to Jake. He's going to take you through an example of the creation tool and give you a video demonstration.
Yeah, thanks, Derek. So like Derek mentioned, we're going to take a little bit of a deeper dive into the creation tool, talk about what's involved with building a reduced order model using the Veritrek creation tool, and taking a look at a short demo to see what the software looks like and kind of the steps involved with working through the ROM creation process. But first, I just kind of want to talk a little bit about the main steps involved with building a reduced order model using the Veritrek creation tool. So like Derek mentioned before, we start with our high fidelity thermal desktop model. And Veritrek interacts with thermal desktop using CRTech and Thermal Desktop's OpenTD API If any of you have heard of that or are familiar with that, that's what Veritrek is leveraging right now. So the first thing Veritrek's going to do is import the necessary model characteristics that we need from our underlying thermal desktop model. So symbols, registers, nodes, K-sets, etc. Once those are imported into the creation tool, the user is able to select and set up the inputs and outputs that they want for their ROM. Once the user does that, Veritrek takes over in a pretty automated fashion. Veritrek will go ahead and create the necessary training runs for us. It'll generate that training data by performing each of those training runs in Thermal Desktop, and then running that training data through our data fitting algorithm to complete the ROM creation process. Once the ROM is created, the last step involved with working through the Veritrek creation tool is a ROM testing step that's kind of built into the software that allows you to directly compare ROM prediction results to measured thermal desktop model results for kind of random, unique test runs that Veritrek will create for us. So you can use that step to evaluate and look at the accuracy of your reduced order model. So the end result of the creation tool is a fully created ROM that we've tested, we've looked at its accuracy, and we're comfortable with its prediction capabilities. So with that, I'm going to jump into a short video demo of myself just working through this ROM creation process inside of the creation tool. So this is just a kind of screen capture video that I'll be talking over live, just so you guys are aware. So we're gonna, as I start this video, I'm gonna start in our thermal desktop model. We're gonna be building a reduced order model from this 6U CubeSat thermal model. So you can see some of the different components and submodels that we have included in this thermal model. We've parameterized our model using thermal desktop symbols, and we've just organized the inputs and registers we're going to use into Veritrek and registers tabs. And then K-sets. So we have two different K-sets we're going to look at for this example that just control the material type for our CubeSat deployable radiator. So now we're going to jump into the Veritrek creation tool, and the first thing we're going to do is give our ROM a name and then choose our underlying thermal desktop model. So we just select the .dwg file. The user clicks apply, chooses a save location, and then for the first time, Veritrek opens up the thermal desktop model, and this is where it's importing all of those model characteristics that we need to build our ROM. So now we can move on to the Inputs tab. And this is where a user will select and set up the symbols that they want to use as input factors for their ROM. So you simply select the symbols here on the left. They show up in this table on the right. And this table on the right is where the user is able to define the design space range for each input factor. So the user specifies the minimum and the maximum value, as well as if they want to evaluate that input factor in a continuous fashion or look at discrete values between the minimum and the maximum. Once we select and set up the symbols that we want to include as inputs, we also choose the K-sets that we want included in our ROM as well. So once we do that, we can move on to the Outputs tab, and in a similar fashion, this is where the user selects and sets up the output responses that they want. So we can look at individual nodes, registers, entire node groups. We select them on the left. They show up in this table on the right. And since this is a transient analysis, we're going to look at the minimum and maximum temperature and maximum register values for our selected output responses. So once the user sets up the inputs and outputs, Veritrek just performs a quick check to make sure nothing's changed in our thermal model. And then we can move on to the ROM Setup and Summary tab. I won't get into all of the details involved with this tab. We do provide those in our user manual. But this is where the user specifies the number of training runs that they want to use for their ROM creation. We're going to use the default values here. Veritrek creates those training runs for us. And then all the user needs to do is click the Start ROM Creation button. And Veritrek takes over in an automated fashion, It'll pass each one of those training runs off to Thermal Desktop, where that run will get performed. Veritrek will pull out the necessary output information we need from that run, and that gets stored as a single training data point. And that process repeats until we end up with our entire training data set. Once we have all of our training data, the user just needs to click the Generate Fit button, and Veritrek will automatically run that training data through our data fitting algorithm to complete our ROM creation. Like I mentioned before, the last step involved with the creation tool is to test that ROM that we just created. So Veritrek will create some unique test runs for us, and in a similar fashion, the user just needs to click Start ROM Testing. These unique test runs will each get performed in Thermal Desktop, and Veritrek will save the necessary output information from those test runs, and then we're able to directly compare ROM prediction results to those measured Thermal Desktop model results for our test data. And so we end up with these result plots, one for each of our output responses, where we're directly comparing ROM prediction results to measured Thermal Desktop model results. Our test data is the red circles, and so we want those to fall along the green diagonal dashed line that represents a perfect ROM prediction of our underlying thermal model. So you can see in some cases, we don't fall exactly along that ideal line. And so using a combination of these test plots along with the numerical data we provide in the form of mean of the residual and standard deviation of the residual, it's really up to the user to determine if the ROM is accurate enough for their application. Since we're doing okay on time, we have an addendum to this video that we'll get to in a couple of seconds, but we're going to pick the video back up by taking the example that those results we just looked at, let's say they weren't accurate enough for what we were wanting. There's a new feature included in the latest release of Veritrek, that's this ROM improvement feature that essentially allows us to add more training data to our already built ROM to improve the ROM accuracy. And so everything works in a similar fashion to the ROM creation, where we can just add additional training data. Veritrek will generate that training data for us, and we can see the updated result plots here. And since we added more training data, our ROM becomes more accurate. And so a user can kind of keep adding more training data until they're comfortable with the ROM accuracy, and they're ready to go ahead and use it in the exploration tool. We also have an exciting new feature that will be included in the next release later this fall, and that's a ROM parallelization feature that essentially allows you to split up training data runs to multiple creation tool files. And so you can load those creation tool files across multiple machines or on the same machine, depending on how your Thermal Desktop licenses are set up. But this essentially allows you to generate your training data in parallel and then merge everything back together at the end so that it's, comes back together as one reduced order model. But as you're probably aware or kind of picking up on, the time investment of generating the training data is kind of the biggest cost to creating a reduced order model. And so this ROM parallelization feature is something that has been brought up to us a lot, and it's something we've implemented to help reduce that ROM creation time, and it should be rolled out in our next release here pretty soon. Okay, so going to jump back into the slides. These next two slides just kind of highlight a couple of customer success stories. We wanted to kind of share a little bit about how some of our customers are using the Veritrek software. So again, we'll talk about how to perform some of these rapid thermal analyses in the exploration tool presentation tomorrow. So these results that you're seeing, a reduced order model was built with the creation tool, and then these analyses were performed in the exploration tool. So this first slide is just highlighting some of the work that we've done, as Derek mentioned, with the NASA JPL Mars 2020 helicopter team. They are planning on using Veritrek for some mission operations once the helicopter is on the surface of Mars, which I believe is supposed to be in February of 2021. So coming up here soon, we're really excited about that. This slide is highlighting some of the work we did with JPL a couple of years ago when they were looking at thermal design sensitivities of the Mars helicopter thermal design. And so they used Veritrek to do that work. They built a reduced order model that included 6 input factors, 36 output responses. We can see some of the test data generated by the creation tool, from that reduced order model. So based on kind of the requirements of the JPL Mars helicopter team, they wanted an accurate ROM. We ended up using 144 test points and, got the mean of the residual less than 1 degree Celsius in this example, standard deviation, right around 1. So just an example of kind of the ROM accuracy involved with JPL's Mars helicopter ROM. For this work back in 2018, they used Veritrek to do 2 things, to evaluate the thermal sensitivity involved with the survival energy of the Mars helicopter thermal design. So they really wanted to understand, how the survival energy value could change as some of their input factor values, could fluctuate during mission operations. So they used Veritrek screening analysis to look at the relative impact that each input parameter had on the survival energy. And they used that information to make a small tweak of lowering the battery set point temperature to accommodate for other uncertainties and make sure that the survival energy was at a place that they were comfortable for the mission. They also used Veritrek's optimization analysis to, and I guess in a design verification fashion, to make sure that at any point, at any place in the thermal design space, they would still meet component temperature requirements. And so the optimization analysis allows a user to quickly interrogate a design space with thousands of possible combinations. And so we end up with this design envelope plot. We have a battery minimum temperature and battery maximum temperature on our 2 axes. And so we could, if there were temperature requirements for our battery, we could look at which areas of the design space we fall outside of those requirements and make adjustments to keep everything within our allowable temperature requirements. This slide just highlights some of the work that the Sierra Nevada Corporation thermal team has done, what they've used Veritrek for with their Dream Chaser cargo thermal model. The actual thermal desktop model and ROM data aren't available for public release right now, and so we kind of put together just a quick representative example, using one of our demo or tutorial models to kind of talk about, the process that they're using and kind of try and show a representative example of what they're using Veritrek for. So they're using Veritrek to screen a large number of cases very quickly. So they have temperature requirements and, need to prove that the thermal design meets those temperature requirements in hundreds of different cases or hundreds of different scenarios. And so typically, to kind of solve this problem, they would sweep through a few discrete points, so generate a lot of these kind of low fidelity parametric sweep plots to observe kind of the minimum and maximum values for their output responses of interest. And once they locate the minimums and maximums, they can kind of focus their design efforts on alleviating those to make sure the component temperatures or the host vehicle temperature meets the flight temperature requirements. And so they used Veritrek and specifically our factor sweep and surface plot analysis features to do this because they could generate a response surface like what's shown in the lower right that includes thousands of data points, multiple input factors on the same plot. And so with this response surface plot, we have the same information, this kind of low fidelity parametric sweep plot. We have that included, but with thousands of points also included, it can really kind of speed up this design verification process, locate the minimums and maximums in the design space very, very quickly, and kind of use that information to focus design efforts on optimizing those areas of the design space. Okay, and so with that, I'll turn it back over to Derek for the last couple of slides.
Yeah, thanks, Jake. So this slide here just, we saw some examples of using Veritrek at different stages of the thermal design life. You know, we saw some of the NASA work that was used for kind of screening analysis that might be done as we're in the detailed design. And with NASA JPL, with their Mars 2020 helicopter work, they were looking to, as Jake had mentioned, trying to understand, you know, which thermal drivers were, you know, driving some of their survival heat or energy outputs. We also, as we'll hear tomorrow morning, they're also using that as a mission ops tool. So kind of late in the design life, they're going to use it as a day in the life tool for trying to plan for next day mission ops when they get to Mars. So what we found as we've been working with a number of different customers is that really Veritrek has been useful throughout the design life. You know, whether it's early in the design where we're trying to do design trades, or with as the design matures, we have detailed design, or even thermal testing, we have a correlation analysis feature that'll be coming out that will hopefully, you know, allow you to rapidly correlate thermal models to test data. And then, as I mentioned earlier, with the mission ops, you know, late in the design life, we also have seen a value of Veritrek then. Jake, we can move to the next slide. And so, you know, where are we going with Veritrek? We have Veritrek 4.0, which will be coming later this fall. One of the big additions this fall is that we're going to add ROM parallelization. And so that, you know, that's, as Jake had mentioned earlier, ROM creation is heavily dependent on running thermal desktop models, and any way that we can make that more computationally inexpensive is a good thing. And so parallelization is kind of the low-hanging fruit. You know, if we can run models or simulations on multiple machines simultaneously, we really cut down that cost. And so that will be a feature that will be available this fall. And then what are we looking at in the future? Well, there's a couple thoughts here. These certainly aren't the only thoughts of things that we're actively working on, but one of those are transient ROMs. And so, you know, can we capture a reduced order model that captures basically the time history of temperature? So basically a temperature versus time plot. Can we do that under multiple input factors? And the answer is we've done some testing early on, and the answer is yes. It's for us. It's more how do we integrate that into the Veritrek tools? When do we do that? And so we're kind of looking through that. Some of the applications there that we've been working with people on is model predictive control, for example. You know, if you want to predict out in the future, maybe a minute or two to kind of see where you might be, and you may want to change your control scheme based on that. You know, a reduced order model could be very valuable in those cases. Another area that we're doing some active development is multidisciplinary reduced order models. So everything in this presentation has really been talking about thermal reduced order models, but you know, the approach can also be applied to other disciplines. So some of the Mars 2020 work, there was a power component that's very important and very interrelated with thermal. So, you know, perhaps you could create a power reduced order model, and then how do you couple those two reduced order models? And that's something that we are doing some active development on this fall, in fact. So, you know, we'll be looking at those types of approaches and hopefully be rolling out updates in the near term. Jake, you can move to the next slide. Yep. So with that, that's kind of the extent of our talk. We did have a couple questions online, but before we get to those, I just want to mention that number one, congrats to the Mars 2020 team. You know, we had a successful launch a few weeks ago. So excited for NASA JPL and everyone involved. You know, we're happy to be a small part of that effort. If you are interested in Veritrek, if you feel like, you know, this is something that that might be of interest to you, we can get you started on a free trial. Feel free to reach out to Jake. His email address is right there on the screen. Feel free to reach out to him. If you just want to talk further about your particular applications, yeah, feel free to reach out to us. We'd be happy to get on the phone and just, you know, talk about your specific applications. With that, I'm going to go to some of the questions that are on the chat. One of them is, can we disclose how many nodes in the Dream Chaser model or order of magnitude? No, we can't. Sorry. Next question. So even geometry changes like radiator dimensions can be included since the training runs include the radiation runs that account for the updated geometry. Yes, that's correct. So some of the input parameters or input factors that we've included in reduced order models, it has included geometric changes, so the change in a radiator area. We've included optical properties, so changes in emissivity or absorptivity. We've looked at changes in thermophysical properties, so something like thermal conductivity. We've done some fluid models where we've changed fluid properties, so maybe changed from a Galvin fluid to a dinoline fluid, for example. So those are also some of the input factors that we have included in reduced order models. So it's kind of the rule of thumb that we tell people is that if you can include it in your thermal desktop model, we can probably include it in the reduced order model. So just start thinking, you know, can I get it in my thermal desktop model? And if I can, yeah, we can probably reduce that down. So with that, I didn't have anything else. I think what we will do on our side, we'll just sit tight and you know, monitor the chat window. If you have any questions, feel free to yeah, just type them in the chat, and we'll hang out and respond to those as necessary. And if not, feel free to email Jake or myself. And with that, thanks for your time. It's been a pleasure, and we will be providing another talk tomorrow morning at 9 Central on the Veritrek exploration tool, and then at 10 a.m. Central, it'll be a short presentation on some of the work that we've done with the Mars 2020 helicopter. Right. Thanks, everybody.
Okay, thank you so much for your talk. We will leave this room open until about 5:30 if questions continue to flow until then. Otherwise, that's the end of the first day of TFAWS. Thank you for attending. We do have one question in chat for you guys on how long it takes for the creation tool to run versus number of nodes in the model.
Yeah, I saw that. Great question. So that's creation tool is heavily dependent on the fundamental thermal model and how long that takes to run. And in addition to that, it also depends on the number of input factors that you want included in your reduced order model. And so let's say you have a relatively small thermal model that runs very quickly, and you only want a few input factors. That's a reduced order model that would take very little time to create. But let's say now on the flip side, you have something that you have a very large thermal model that takes a long time to run, let's say hours to days, and you have multiple input factors, maybe 10 input factors. That's going to take quite a bit of time. Typically what we tell people as a kind of a rule of thumb, just a starting point, it doesn't hold all the time, is that if the number of training data runs required is about 2 to the n, or n is the number of input factors. And so as the number of input factors grows, the number of required training data runs grow also. And so each training data run is also dependent on the runtime of your thermal model. And so let's say you had 6 input factors, and your thermal model took 1 hour to run for each training data simulation. It'd just basically be 2 to the 6th would be the number of hours it would take to generate the required training data to create the reduced order model. The actual data fitting step is small relative to the cost of generating the training data. So hopefully that answered your question. If not, feel free to type in another question in chat. Question came up, what's the largest thermal desktop model that you've had to work with, node count-wise? Oh, really good question. I'm sure it's on the order of a few thousand nodes, possibly more. I don't have a great answer for that. There's certainly some cases where if you have a thermal model that's, I don't know, maybe 100,000 nodes, for example, I'll just throw that out as an example. Maybe it takes multiple days to run a single simulation. Unless you have, you can leverage heavy parallelization, Veritrek might not be a great application for you just because of the cost to generate the required training data. Not to say that it wouldn't work, but you have to weigh the computational costs of generating the training data to get your ROM. I will have to get some thought on the largest thermal desktop model that we've worked with. That's a great question.
Yeah, but just to reiterate, you know, the number of nodes doesn't necessarily have an impact on ROM creation time. It really is the amount of time it takes for one thermal desktop run. So obviously that's going to take, you know, longer with a larger node model, but all Veritrek cares about is, you know, the time it takes to complete one run. And something that, you know, a lot of our customers do is because of kind of the automated nature of Veritrek generating the training data, what a lot of people do is they set up their ROM and click go on a Friday afternoon, you know, and let Veritrek run and generate the training data, you know, for the couple of days over the weekend. And in a lot of cases, by the time the user gets back Monday morning, you know, most, if not all, of the training data has been complete. So Veritrek can run, you know, in the background. You can pause and resume ROM creation depending on, you know, the thermal desktop licenses that you have available. But a lot of our customers do leverage the weekend for some of the higher fidelity ROMs or the larger ROM creation times.